just to see if everybody is here. So, is Francesc here?
Oh, yes.
Yes?
Yes, I'm here.
Hi, Francesc.
Hi, Francesc.
Hello. Hi, Florence. So, I already see you.
Hello.
Donatello?
Es-tu avec nous, Donatello?
Oui, je suis là.
Salut.
Bonjour.
Tu vas bien?
Oui, très bien, merci.
Ok, ici donc il y a Paul, Florian, Sébastien et moi-même, moi. Je pense qu'on est au complet, yes, I think we can start.
Okay, so I propose to start. Hi, Linlin. We are here today to see your presentation of your PhD work. The title is Bridging Graph and Kernel Space, a Pre-Match Perspective. The jury is made of Professeur d'Algébrique from Télécom Paris, Donatello Conte from the University of Tours, Francesc SERRATOSA, which is Professor at Tarragona, and Florian YGER, which is Assistant Professor at Paris-Dauphine. Your supervisor are Paul Onen and Benoît Galzer, and I am Sébastien. I have the pleasure to be the president of your jury. So you have between 40 and 45 minutes to present your work, and after we will have a period of question and answer.
Okay.
So, when you want.
Okay. Okay, so good morning, dear jury members. Good morning, everyone. Thank you very much for coming to my defense. My name is Linlin Jia. I'm a PhD candidate from LITIS lab in INSA Rouen Normandie, and I am supervised by Professor Bolonen and Professor Galzer. And the title of my presentation today is Bridging Graph and Kernel Spaces, a Pre-Image Perspective. I will proceed my presentation today in 5 sections. First, I will introduce the background, the motivations, and the contributions in my work, and then I will detail these contributions in 3 sections, and finally I will conclude my contributions and give future perspectives. Now let's start with the introduction. My work focuses on the graph datasets. In real life, there are many kinds of datasets which can be modeled by graphs. These datasets have some common structures. First, they have some entities which can be modeled by vertices of the graph, and there are some relationships between these entities which can be modeled by the edges of the graphs. Let's take the molecules here, for example. In a molecule, we can model the atom as the vertices of the graph and the chemical bonds as the edges of the graph. We can also assign symbolic and non-symbolic labels to both vertices and edges. For example, we can consider the type of molecules as the vertex label and the type of chemical bonds as the edge label. Now, with all these graph datasets at hand, we want to perform all kinds of tasks on them. For example, the regressions, classifications, etc. So this leads us to 2 questions. First, when we have a graph at hand, how can we acquire features and spaces, features and properties from them? And the second question is, when we have the design features and properties, how can we construct a graph corresponding to that? My research have developed methods for both of these questions, and these methods have taken advantage of the state-of-the-art machine learning methods. The machine learning methods have been achieved success recently in many applications and domains. In principle, the machine learning method takes input data and extract patterns, features, and properties automatically from them. However, traditionally, the machine learning methods are performed on Euclidean space, which is continuous, and the element dimension of this in this space are often fixed. Compared to that, the graph space is discrete, and in each graph, the number of vertices and edges may be arbitrary. Moreover, we can assign different symbolic and non-symbolic labels to both vertices and edges. Moreover, even if we have two graphs with different order of vertices, these two graphs may be isomorphic. This brings a lot of difficulties to use the machine learning methods for graphs. So, how can we bridge this gap? Now we can introduce several methods. To bridging the gaps, the first thing to do is to construct a similarity measure between the graph data structure and the machine learning methods. Here we introduce three ways to do that. The first one is the graph at a distance, which is performed directly on the graph space. It measures the dissimilarity between the two graphs by the distortions when transforming one graph to another. The second one is the graph embedding, which maps the graph to a feature space, where the similarities between the two graphs are compared there. Among these methods, the graph kernels can implicitly embed graphs into a feature space, where we can preserve as much as information as possible. Now we have graph kernels at hand. We can extract features and spaces from the features and properties from the graph and map the graph to a kernel space. And this corresponds to the first question we asked. And we have a lot of applications to that, including regressions and classifications, etc. On the same time, we also want to ask another question. When we have an element in the kernel space, how can we construct a graph corresponding to that element? This is the so-called pre-image method and corresponds to the second question we just asked. The application of this problem is also numerous, including molecule synthesis, drug designs, and etc. Now with all this knowledge at hand, I can now introduce my contributions. First, in the kernel space, we did a thorough study of the comparison between the graph kernels based on linear patterns. We proposed methods to reduce computational complexity of these graph kernels. And in the graph space, we studied the stability of the graph at a distance. With the help of these two research, we then propose a pre-image method by aligning the aforementioned two spaces. We propose to use an iterative algorithm to construct the graph pre-image. On the same time, we also propose a method to learn at the cost of the GED for the regression problem. Finally, we implement all this method in an open source library. Now, let's begin with the first contribution, graph kernels based on subpatterns. We can consider the graph kernel as a similarity measure, and one of the well-known diagrams to do this is to first decompose the two graphs into subpatterns, and then we measure similarities between each pair of subpatterns and combine them to construct the similarities between the two graphs. This diagram can be used in all kinds of data sets, and this is where the R convolutional kernel is constructed. For example, let's take the banana, for example. Let's say we want to measure the similarities between the two bunches of the bananas with respect to the calories contained in them. First, we decompose each bunch to individual bananas, and then we measure similarities between each pair of the bananas by say a linear kernel, and then we combine these measurements and construct the similarity of the two bunches. When it comes to graph, we can simply replace bananas with the substructures contained in the graphs. Here we have the linear pattern, the nonlinear pattern, and the cyclic patterns. And this leads us to my first contribution, a thorough study of the graph kernels based on linear patterns. There are two kinds of linear patterns, walks and passes. Walk is a sequence. In principle, the walk is a sequence of vertices and edges, and the pass is a walk where each vertex will appear only once. In the graph kernels based on walks, we first have the column walk kernel, which considers all the walks in the graph. Secondly, we have the marginalized kernel, which introduces randomness into the procedure. And the last one is a generalized random walk kernel, which is a generalized framework containing all the two aforementioned kernels. There are 4 ways to compute this kernel. Each of them corresponds to a graph kernel. Then, in the graph kernels based on passes, we first have the shortest path kernel, which measures similarities between each pair of shortest passes in the graph. And then the graph structural shortest path kernel, in addition, considers vertices and edges along the shortest passes. Finally, the path kernel measures the real passes in the graphs. Finally, we also consider 2 graph kernels based on nonlinear patterns, the tree-let kernel and the WL subtree kernel. The first one is based on the similarity measure of a set of a priori defined subtrees, and the second one is constructed by an aggregative procedure. All these graph kernels can tackle all kinds of graphs. For example, they can tackle symbolic and non-symbolic labels in vertices and edges. However, the time complexity to compute these kernels are quite high, even for the best case here. And this has become an Achilles heel of the graph kernels. So to tackle this problem, we have proposed methods to speed up the computation of the graph kernel. The first one we proposed is an extension of the fast computation of the shortest path kernel, aka the FCFP method. When we computing the shortest path kernel, we first need to construct the shortest path graphs for each of the original path graphs. And here the label of the edges is the shortest path between the 2 vertices. After that, we compare the similarities between each pair of the shortest passes using a kernels between passes, here the KP. And then we combine these measures and construct the shortest path kernel. Notice here when we try to compute kernels between passes, we need to compute the kernels between the vertices, KV, and the kernels between the edges, KE. Here, the kernels between each pair of vertices may be computed multiple times during the procedure, which means we introduce the redundancy of the computation. In this example, the kernels between each pair of vertices have been computed 3.6 times in average. So to reduce this redundancy, we propose to use the FCSP method in this to compute the shortest path kernel. Before computing the path kernels between passes, we first construct a vertex kernel matrix, which contains the kernels between each pair of shortest path of the vertices, and then we use this matrix to compare the kernels between passes and construct the shortest path kernel. In this way, the kernel between each pair of vertices will be only computed 1 time during the whole procedure, thus reduce the the redundancy of the computation. We also extend this method to kernels between edges and to structure shortest path kernel. This figure shows the advantage of our method. Here the blue dot represents the naive computation and the red dot represents our method. As we can see, the FCSP method dominates the performance, where for the shortest path kernel, it is more than 28 times faster, and for the structure shortest path kernel, it is more than 37 times faster. The second way to speed up the computation is to use a tree structure for the path kernel to store the passes. When we try to compute the path kernel, first we extract the passes from each of the graphs, and then we compare similarities between each pair of passes. However, notice here, each vertex and edges may be considered multiple times during the procedure. For example, here, the vertex 1 is considered 3 times. So if we save these passes directly in the memory, it may cause a redundancy of the memory. To tackle this problem, we propose to use the tree structure to store the passes in the 2 graphs. The tree is also known as a prefix tree. For example, we want to store a set of strings in a tree. First, we extract the prefix from each of the strings, and then we combine this prefix to construct the tree. In this way, each of the prefixes will only be stored 1 time in the tree structure. Similarly, we can use this principle to store passes in a graph in a tree structure. First, we extract passes from a graph and construct strings by the labels of vertices and edges along these passes. And then we store these strings to the tree structure. When we try to extract a path from the tree, we can simply go through this path, and this will only take linear time. As we can see here, this figure compares our method with the naive method, where the dot line represents to store the passes directly in the memory, and the solid line is our method. As we can see here, our method can save methods more than 55 times and by avoiding swappings between hard disks and the memories, it can also save a lot of time. So with the help of all these methods, we can now analyze the performance of the graph kernels on real-world datasets. We consider datasets with different kinds of substructures, linear ones, nonlinear ones, cyclic ones. These datasets can have symbolic and non-symbolic labels on vertices and edges. They cover tasks of regressions and classifications. And the graph size of these datasets varies from small ones to big ones up to hundreds of vertices and edges. We can have some interesting conclusion from our analysis. First, we can see that when a dataset is labeled, it can achieve much better accuracies than a labeled ones. Secondly, among these labels, considering the non-symbolic labels can have a higher accuracy, which is almost 1 times. We also compare the graph kernels based on linear and non-linear patterns. Here, the 2 tables are the accuracies and time complexities of these graph kernels. Notice here, the last 2 columns corresponds to the ones based on nonlinear patterns, and the others are based on linear patterns, whereas the ones in the gray borders are the ones based on passes. And the grayer the color, the better the performance. We can see here that the graph kernel based on linear patterns can achieve quite a good performance on graphs with non-linear patterns, which is even competitive with the graph kernels based on non-linear structures. Finally, we also implement all these graph kernels in our library. So in conclusion, in this section we did a thorough study of the graph kernels based on linear patterns. We have found out that graph kernels based on linear patterns can achieve a successful results on the graph kernels with nonlinear structures, which is competitive to the graph kernels based on nonlinear patterns. We propose several structures to speed up the computation of these graph kernels. We also found out that using the non-symbolic labels for graph kernels can have a higher performance. So for now, we have tackled the first question, how to extract features and properties from a graph. So how about the second one? How to construct a graph corresponding to these features and properties. As we know that graph kernel is not performed directly in the graph space. So it can be difficult to use them to construct graphs directly. So we propose to use the graph edit distances to do the job. And this leads us to our second contribution. In contrast with the graph kernel, which is performed in the kernel space, the graph edit distance measures the dissimilarities between the two graphs directly in the graph space. The dissimilarity is measured by the distortions when transforming one graph to another. During this transformation, 6 fundamental operations is considered, namely the insertion, the removal, the substitution of vertices and edges. Along these operations, we can construct a sequence of the fundamental operation, which we here denote as pi, and is called an edit pass. Then we can assign a cost to each of the possible edit passes. And the graph edit distance, GED, of the two graphs is defined as the minimum possible cost of the edit passes. So how do we construct this cost of the edit pass? First, we define the cost functions for each of the fundamental operations. And then we combine these functions, and then we have the cost of the edit pass, and further have the GED. In practice, we often set the edit cost function to be constant, which means we don't consider the amount of the difference between different labels. In this way, we can reduce the edit cost function of each operation to a multiplication of n and c, where n is the number of occurrence of this operation, and c is a cost constant assigned to that operation. Let's denote omega as the vector of the number of occurrence of the operation, and c as a vector of the cost constants. Then we can write GED as a multiplication of omega and c. Now we have the two to measure the dissimilarities between the two graphs at a constructed graph using the edit operation. But the graph edit distance have very high computational complexity. In the literature, many heuristics have been proposed to approximate the GED. As the GED can be considered as a quadratic problem, the IPFP and its multi-stat counterparts MIPFP are proposed to approximate the GED. In this way is a more accurate way and the state of art and achieve the state of art performance. Another way is to reduce this problem to a linear sum assignment problem with error corrections, and this is where the bipartite has become a representative heuristic to approximate the problem. Now we have tackled the time complexity of the GED. A new problem is induced by the heuristic. As approximations are not optimal, the randomness may be introduced during the computation, and this may lead to instability of the computation. So it is important to study the stability of the heuristics before using them. And this leads us to our first contribution of the section, the study of the stability of the GED heuristic. First, we have defined a measurement of the stability. Here we use a relevant arrow to measure the instability of the two graphs of the GED heuristic. In principle, this arrow measures the difference between the GED computed by the heuristics and the true GED, and then averages them over the trials. We studied the relationship of the two factors with the stability. The first factor is a number of random initial candidates of the GED heuristics, which is also known as the number of solution or denoted as n. Notice here, when we use different random initials, we can have different GED values. This figure shows that as the number of solutions increases, the arrow decreases and the stability increases. The second factor is the ratio between the added cost between the vertex and edges. And similarly, this figure shows that as the ratios increase, the arrows decrease and the stability increases. This study helps us to determine the value of the parameters to choose before using the heuristics. Now, with the help of this study, we then propose a method to learn the added costs for regression problems. In the literature, there are two kinds of ways to determine the costs of the GED. The first one is to set them manually, which is known as the expert cost. This way, we can have a domain knowledge implied a priori, which is its spare but also its soft spot. Because this cost has to be known a priori, which is not always the case, and it's very hard to generalize to other datasets and applications. Moreover, data information may not be well explored during this procedure. So another way to do this is to learn the costs. In this way, the added costs are tuned automatically for each specific task. However, the literature to this way is quite limited. Some of them have high computational complexity. Some are restricted to strings and trees. Some require grand truth mapping. So to tackle this problem, we propose a method to learn the added cost by aligning the graph at distance and the distances between the targets. So first, to align the graph space and the target space, we want the distance between each pair of graphs to be as close as possible to the distance between the distance of the corresponding targets. The distance in the graph space, we use the GED as the distance in the target space can be Euclidean or Manhattan spaces, etc. And this leads us to minimization of some square of the difference between these two distances. Notice here, the C and omega are both parameters to optimize. To solve this problem, we propose an alternative operational strategy. First, we fix the cost C, and then we use the heuristics to compute the GED, the added path, and the corresponding omega. Then we fix omega, and this problem is reduced to a constrained normal linear problem, which can be solved by a solver, and then we can have a new cost C. We repeat this procedure until we have the optimized cost C. We examine our method on two datasets, a cyclic and alkane. These are molecule datasets which corresponds to a regression problem with their boiling points. After computing the GED, we use the key nearest neighbor regression method to tackle the problem. We use two heuristics to compute the GED and two layers cross-validation to measure to estimate the performance. And the key value of the nearest neighbor is optimized in the inner CV. Now we compare our methods to three other state-of-art methods. Here, the red bar is using the random cost. The blue bar is using the expert cost. The green bar corresponds to a state-of-art method which uses a genetic algorithm to optimize edit cost. And the purple bar is our method. Here we measure the performance with the RMSE, so the lower the better. As we can see here, our method have outperformed all the others on all the circumstances. So after using the method, we can obtain optimized costs. We can have some interesting conclusions from these costs. First, we can see that the costs of deletion and the insertion are almost similar, which means that these two operations is quite symmetric. The second one is that the cost of deletion and insertion are bigger than the cost of the substitutions, which one of the theories to explain this is that the number of atoms in a molecule is more important than the atom itself. Finally, we go back and examine the stability of our method. Here, the different color implements, different color represents different data sets. The X mark represents the ones using the expert kernel, expert costs, and the diamond mark and the circle mark represents our methods with different distances between targets. We can clearly see here that our methods corresponds to a higher ratio of the costs between the vertices and edges, which corresponds to a higher error and lower error and better stability. Again, we have implemented these heuristics in our library. We also implement a media graph estimation method, which will be used to construct graphs for the next section. So, in this section, we have studied the stability of the GED heuristics with respect to two factors, and then we propose a method to learn the added cost for a regression problem. Finally, our experiment shows that our method can have a promising results. By now, we have the tools to construct the graphs, which is using the GED by the added operations. Now we can go to our next contribution, the graph pre-image methods. Let's quickly review the problem. First, we have a graph kernel, which maps the graph into a kernel space. This corresponds to the first question we asked. Now we want to consider the second question. When we have an element in the kernel space, how can we construct a graph corresponding to that element? This is the so-called pre-image problem and corresponds to the second question we asked. However, unlikely in the literature, the method to solve this problem is quite limited. Here, we introduce the baseline method proposed by Bakia. This is a method based on the random iteration on the kernel space directly. However, it is restricted to a small number of edges without the labeling information. Also, the randomness during this procedure will lead to a decrease of qualities and a high computational complexity. So to tackle this problem, we propose a framework where we use a GED as a direction to construct a graph and intuitive methods to construct the pre-image. We propose three variations of this framework. The first one is with a random added cost. The second variation is with expert costs. And the third variation is with the optimized added cost, which is computed using a method we proposed and will be detailed in the following parts. Our framework is based on a hypothesis. When we have an element in the kernel space, we can consider this element as a combination of its neighbors. Let's say we want the preimage of the mean element in the kernel space. Then we can use the media graph to approximate this preimage. A media graph is a graph which corresponds to which have the shortest sum of distance to all its corresponding neighbors. And we use the state-of-art method to construct the media graph based on GED, which is proposed by Rovira. Let's first find the best media graph from the dataset, this one, and then we compute the graph at a distance between this graph and all the other graphs in the datasets. During the computation and the edit pass, the C here is replaced by a label A and two label D in these two graphs and is removed in these three graphs. So we replace the label of this vertex with D because the D appears most of the time in the other circumstances. And then we do the same procedure for all the vertices and edges in this graph. And the graph is then updated to a better estimation of the media graph. When it comes to a non-symbolic labels, the label can be we replace the label with the mean of the possible candidates. And this in turn justifies our hypothesis. So let's take a deeper look to the last variation, how to use optimize the cost. We propose to use similar methods that we used in the regression problem. First, we want to align the graph space and kernel space. We want the distance between each pair of graphs to be as close as the distance to each pair of the corresponding elements in the kernel space. And the distance in the graph space is again using the GED, and the distance in the kernel space here can be computed by the graph kernel using this formula. And this leads us again to a minimization of the sum of the square difference of the two distances. And here again, the C and O got both the elements parameters to optimize. And we use an alternative iteration procedure to solve this problem. First, we fix C and use the heuristic to compute GED and omega. And then we fix omega, and this reduces problem to a constrained linear problem with a linear programming problem which can be solved by the solver, and this gives us a new C. This procedure will repeat until we have the optimized cost C. After we have the optimized costs, we then propose an alternative iteration procedure to construct the graph preimage. First, we choose a candidate graph G hat from the dataset. This graph can be chosen randomly or by a best one. And then we compute the graph at a distance between the G hat and all the other graphs in the dataset using a heuristic, and the corresponding added pi hats. Then we fix pi hats, and then use the aforementioned method to update the media graph. And then we can have a new G hat. We repeat this procedure, and finally we can have the designed graph preimage, the G star. Now let's examine our method on the letter dataset, which is the handwriting letters, which contains handwriting letters with different distortions, and the nodes of the graphs are labeled with the positions of its positions. We use two heuristics to compute the GEDs, and the size of media set is set to 150. Now in this figure, the column DH shows the distance between the constructed preimage and the true preimage in the kernel space. As we can see here, our proposed method using random cost, expert cost, and optimized cost achieves better performance in most of the cases. Especially the optimized costs used here can achieve a competitive performance with the expert cost, which means we can have good enough results without even any knowledge a priori. We can also plot these letters on 2D coordinates. We can see here our methods have a better, is more legible than the other methods. Finally, we also implement our preimage method and the baseline method in our library. So for now, we have tackled the second question. In this section, we have proposed a new framework to estimate the graph preimage. We have proposed 3 variations with random cost, expert cost, and optimized cost. Whereas the last one, the optimized cost, is computed using a matrix learning by aligning the kernel and graph spaces. And finally, we construct the graph preimage using an alternative iteration procedure. Finally, the experiment shows that our proposed framework can generate better preimage than the other methods. So that's all for my researches, for my contributions. Now let's have a conclusion. First, in the kernel space, we did a thorough study of the comparisons of the graph kernels based on non-linear patterns, and we proposed strategies to reduce computational complexity of these graph kernels. On the graph space, we studied the stability of the GED corresponds to 2 factors. With the help of these 2 research, we then proposed the preimage methods by aligning the 2 spaces. Finally, we also proposed a method to learn at the cost of the GED for regression problems. Finally, we implement all these methods in our open source library, GraphCape-Learn. The future work of my research will follow the same structure. First, in the kernel space, we will try to study the relationship of the graph kernels based on linear patterns and some of the new state-of-art kernels. And it will be also interesting to use other strategies to reduce time complexity of these kernels. On the graph space, we would like to study the stability of the GED with respect to other factors, such as the characteristics of the graph. And then, for the preimage problem, it will be interesting to tackle the convergency proof problem. And we would like to extend this method to non-constant costs. Finally, new frameworks such as graph neural networks may be interesting to use to do the preimage problem. And in the meantime, for the methods to learn at a cost for regression problem, we would like to extend that to classification problems and also to the non-constant costs. Finally, we will enrich our library corresponding to these new works. And this is the publication during my research. And that's all for my presentation today. Thank you very much for your listening. Thank you.
Thank you very much, Linlin. So now we'll switch to the question and answer period.
Okay.
Traditionally, we start with the reviewers of your manuscript. So I suggest to start with Florence d'Alchebuk, if you are okay, Florence.
Thank you, Mr. President. So, first of all, Linlin Jia, I would like to congratulate you for the nice manuscript and the neat way you did on graph